Hey, in the previous video, I introduced joint distribution, marginal distribution, and conditional distribution. And when you learn the conditional distribution, an important following concept is the independence, statistical independence. Statistical independence is actually defined by the joint distribution. This is the full information, and if the joint distribution happens to be the same as the multiplication of two marginal distributions, that means the relationship has no information. The relationship between x, y is nothing, so they are independent. They are no relationship. Or alternatively, if you compare this with something like this, then you can simply, it's easy to understand that the conditional distribution is the same as the marginal distribution. We originally needed to recover the full joint distribution, we needed a marginal and a conditional. But here, by definition, you only need two marginals. That means the conditional distribution equals to the marginal distribution. And if x and y are continuous, you can write it this way. Jay, would you like to say hello? My son is now next to me. So if x and y are both continuous, and if they have PDF, well-defined PDFs, then you can write it this way and this way. So the definition with respect to the CDF goes the same way for PDF. So it's easy to understand. And finally, quantile function is just a small variation from PDF, like CDF, excuse me. So if at a certain point the probability equals PDF equals CDF equals to tau, then if you invert the CDF, then you get quantile function. Roughly speaking, quantile function of tau is it should be y. The quantile function of tau should be the value that returns tau here. So this value must be here. So it's typo. So you can understand that the quantile function is basically the inverse function of the distribution function. However, the inverse may not be well defined. In that case, you need to do some mathematical manipulation. But conceptually, this is general enough, right? And examples are median. Median is the value that returns 50%. Maximum is at 1, minimum is at 0. Or you may think percentiles as a special case of quantiles, or we say like 95% quantile. That means that's top 5% value, or 5% 0.05 quantile is the bottom 5%. So quantile can be understood as a kind of probability distribution. So almost everything you know, you learned from statistics is some kind of probability distribution or expectation. Let me describe the expectation, which is a little bit different from the probability, but depends on the probability because all the random variables are defined characterized by the CDF. So CDF is the definition of a random variable. So expectation should be defined based on the CDF. And it's written in this way. It's an integration. Integrate out and you get this. So this notation is, you may not be familiar with this notation. Why a function is behind D. This is the rigorous notation, but if you don't understand what it means, it does not matter. To understand this, you need to learn measure theory, but that's an overkill, so don't worry about this. You may simply imagine this or this. So maybe this is what you learned. Integration of a function, so expected value of g of x. For example, you can think it as like x squared, or log of x, exponential of x, a function of x, or it could be x itself. So any function of x, to calculate its expected value, you have to integrate that after weighting it by the PDF and integrate. However, this notation is not general enough because PDF is not well defined for discrete variables, for example. So then this definition does not work if PDF is not defined, well defined. So alternatively, you may use this way. For discrete variables, the function g of x, the value of g of x, is weighted by probability mass and summed out. So this is how you calculate expected value for discrete variables, and this notation is a generalization of both because CDF is always well defined. So to make the notation more consistent and more well defined, this notation is developed. That's enough for you to understand this course. And moments are a sequence of expectations. So expectation is a general concept. It is an operator. So when you have a function of random variable, you integrate out using the CDF. And moments specifically imply a certain form of this function. So the first moment is expectation of the first order polynomial, right? It is the mean. Second moment is expectation of x squared. Third moment is about skewness, like expectation of x to the 3. And the first central moment is defined this way. After subtracting the mean, take the first order, and after subtracting, take second order, and after subtracting the mean, take fourth order. The fourth order moment is kurtosis. So that's how you can think about moments. So it's nothing new. Just moments are polynomial functions, the expectations of polynomial functions, simple polynomial functions. It's very convenient measures to see the shape of the distribution. You must be familiar with mean, variance, or skewness. So because they are convenient, easy to understand. When I say the average is something, then it is, what it means, right? So moments are very useful in that sense to deliver information. But in most cases, we focus on mean and variance. Mean and variance is not a complete information. So you need to fully understand what the distribution looks like. You need to know all orders, the moments of all orders, but we focus on the first two moments mainly because normal distribution is so important, and normal distribution uses only those two moments. So if you assume normal distribution, knowing the mean and the variance is enough. And normal distribution is too common, so as a result, mean and variance are usually enough. However, as I said, it does not characterize the distribution, the random variable. The distribution is characterized by the CDF, or if you want to characterize the random variable using moments, there is a different form called characteristic function or moment generating function. I'm not going to define them here, but what I'm saying here is simple moments are not the definition of the random variable. So there are different things or more general functions to define the random variable. Mathematically characterizes the random variables. Okay, and covariance is another kind of expectation, because if you look at the definition, it's clear, everything is expectation. So it's some kind of expectation. And let me define a notation here. So when you have a random vector, then automatically its expected value must be a vector, same dimension. And second moment is defined this way. So when you do x squared instead of x squared in a vector, you have to transpose the second vector so that the resulting second moment is a matrix. So the result should be k by k matrix, and higher moments are not easy. So up to the second moment, it's not a big problem. But when you have third moment, it's very complicated because you have to think about all possible combinations of three numbers. So it's not easy to define with two-dimensional matrix notation. So matrix on paper is only two-dimension. So third moments are not handled here. So this is another reason why we are using the first two moments. It works well with our matrix notation. And then if you look at the second order central moment, the diagonal terms are variances and off diagonal terms are covariances. So we say this as the variance covariance matrix, or simply the covariance matrix, right? It's again just notation, and you must be familiar with these guys. And as I said before, moments may not be well defined. So for example, can be infinity. But I'm not going to consider these kind of cases. I may state the assumption like, say, often we assume that the second moment is finite, which means the second moment is well defined. But in most cases, I'm going to just assume moments are finite because these kind of things are pretty rare. It's very uncommon and not a big problem in our analysis. Maybe in economics, the only example this assumption is relevant is where you think about financial assets with very high volatility. If the assets like stock returns are volatile, too volatile that the variance could be infinity, mathematically infinity. That is possible, but otherwise I have never seen a problem because of this assumption. So we'll implicitly assume that in most cases. And conditional expectation will be discussed in the next video. Thank you.